I'm Hyeonseung from Sungkyunkwan University. Previously, I worked at Samsung, and where most of today's work was conducted. And today, I'm going to present a Radiance casting for a mobile platform. So we see that path tracing is increasingly adopted in high-end games, and they show good examples. And following this trend, mobile devices started to expose hardware ray tracing capabilities. For example, Qualcomm Snapdragon released a demo for ray tracing around 3 years ago, and also Samsung recently announced the neural supersampling or neural frame generation solution for ray tracing scenes. So actually, this solution was also developed by my previous team. And those demos focus on hybrid renderer that supports shadows and reflections through ray tracing. But we wanted to go one step further and to explore path tracing on mobile platform. So in the early stage of our research, we had two major questions. First question is, can you learn path tracing on mobile platform? At the time, there was no path tracing available, so we built our own Qualcomm-based mobile path tracer. And yeah, we checked that it's feasible. Yeah, it learns. It is far from real time, around 4 Hz. So after confirming that, the second question was naturally, can you accelerate the path tracing on mobile platform? So our interest was light in neural Radiance casting. So there are many possible approaches, but our starting point was neural Radiance casting proposed in 2021. So they demonstrate that using neural method, they can actually make it even faster than baseline path tracing. And after that, there are other work like neural instant Radiance casting. And also, recent work demonstrate the implementation on mobile platforms targeting hybrid render with reduced resolution. So our main goal is to really bring those Radiance casting techniques to mobile and apply to path tracing for practical path tracing. And how does it work? So this is the basic principles of the Radiance casting. So basically, in the original analysis paper, they learned the scene with a multi-layer perceptron. So for training, we trace long passes and collect sample data. And then for each sample, we have input features like a position, direction, normal, and roughness. And using the collected Radiance data, we train the neural network each frame. Then for inference paths, we trace shorter passes and use we query the Radiance based on the learned MLP. Yeah, but this MLP is small, so we can efficiently run on high-end desktop GPUs. But yeah, when we implemented this MLP operation on our mobile, it was obviously very slow. It's very trivial, but we wanted to understand what's the bottleneck exactly. So I think this illustration shows the overall picture. So basically in MLP, so we collect the training samples, and so for each sample corresponds to this single entity. So you can think of this as a single entity represent the input pictures of the single training sample. Then for each sample, we predict the Radiance value using all the weights in the MLP. So problem is that mobile GPUs don't have a tensor-like matrix multiplication accelerator. So we need to do them one by one. So this is for forward pass. For backward pass, actually we need to have two major approaches. So one possible approach would be we learn thread for each sample and update the gradient for each weight atomically. Problem is that this atomic operation is really expensive on mobile. So alternative would be to launch thread for each weight. Then we collect all the contributions from all the samples. But problem is that we use almost like 60,000 samples. So it's really hard to make it efficient. Therefore, yeah, we thought that it's natural to shift from a so-called globally coupled chain to locally coupled chain, where we use only few weights for predicting radiance from the training samples. And by doing so, we can now have some like a tractable computational complexity. But still we have two approaches, but this so-called sample anchored approach, we still need to use the atomic operation, and it was still slow. So we decided to go in the second direction. So yeah, based on this understanding, we realized that the proper representation for radiance scattering on mobile would be a plan of cells. So plan of cells was proposed in 2022 as an alternative to NERF, and it represents the radiance field using a sparse voxel grid with a spherical harmony coefficient stored at vertices. And we use a trilinear interpolation to predict radiance field. So basically, we apply this plan of cell representations to our scene. And good thing is that now we can avoid dense MLP evaluation. Also, in path tracing, we know exactly where hit points occur. So therefore, this locality actually enables a very efficient and mobile-friendly online caching. So this is our system overview. So we call it mobile RC. So basically, we follow the same procedures as original NS paper. So for training, we collect the training samples for long passes, and then we train this plan of cell. We have an interpolation of 8 neighboring vertices, and then we update the spherical harmony coefficient using differentiable optimization. And for inference, we use a short pass, and then we use the learned radiance from plan of cells. So we implemented this approach, but we found 2 major problems in the naive implementation. So on the training side, we found that the convergence was really slow. And on the inference side, we also found that inference takes a lot of time. And we realized that it's mainly due to the scattered voxel sets. So we need to carry the radiance for nearby screen pixels, but in voxel space they are scattered. So therefore, it leads to very, very poor memory locality. So to solve this problem for training, we introduced diffuse AMA training method. So basically, for depth of the term, we apply exponential moving average. And for remaining terms, we optimize them using differentiable optimization. And by doing so, we could greatly improve convergence speed. For the inference side, we introduced a grouping and process. Basically, before actually performing the inference, we group the nearby caches. So by doing so, it introduces additional grouping time, but the total time reduced from 140 milliseconds to 30 milliseconds. For implementation, so we checked the two frameworks. The first one is for quality comparison compared to the original NS paper. We implemented on desktop using OutSGI framework. And for mobile evaluation, we built our own custom Vulkan framework that works for both Android and desktop. And all the passes are implemented in computer shaders. So this is quality comparison. So we have two exemplary scenes. So this is the baseline path tracing for one SPP. And by applying our method, we could greatly reduce the MLSE value. And this, we got the comparable values for comparable values with the original NS paper. And we also checked the mobile implementation. So this is extra performance result based on the Samsung Galaxy phone. So for baseline path tracing, we have almost like a 300 millisecond. And since we use short paths for inference space, we have a reduction in tracing, trace and shade part. And training and inference takes around 50 milliseconds, and so we have a reduction in total time. And if we think about the equal quality comparison, if we use 4 samples per pixel, then we could obtain some similar MLSE value. That means that we have this much speed up for baseline path tracing or equal quality path tracing. And this is another result for different scene, and now we have more speed up for equal quality path tracing. So now I will show you the actual demo. Yeah, this is base path tracing. And now we applied our method. So yeah, it's still interactive rate, but yeah, we can go around the scene. And the second video shows time lapse of a Radiance cast. And then please note that this initial screen corresponds to the M loading phase. Yeah, this is time lapse of a training of Radiance cache. It quickly learns the Radiance. And final demo is for dynamic SIG, and this was evaluated on the desktop. Yeah, it shows lighting changes and camera movement, and it relatively quickly adapts to those dynamic changes in the scene. Certainly, you have some limitations. Since we are relying on local representation, we have a limited handling of high-frequency details and abrupt radiance changes. For example, this shows a time lapse of radiance casting from our method and NLC. We have some low-frequency pictures only. And also, we use the fixed grid resolution, so we still need to explore scaling up to larger scenes. Also, we still have we didn't fully address this memory coalescence. So I think we should it requires more systematic approaches to solve this problem. So this is the conclusion. So we propose a plano cell-based Radiance casting, and this representation enables mobile-friendly and locality-aware casting. And to accelerate training and inference, we introduced diffuse EMA training and algorithm and cache grouping and procedure. And we actually demonstrated all the results on our custom mobile path tracer, and we obtained 1.25 average speed up for baseline path tracing, and you could obtain even more speed up if we consider equal quality path tracing. So this is the end of my presentation, and thank you for your attention.
Thanks a lot for the presentation. I was wondering about the path tracing algorithm that you use in practice, and whether you do important sampling of the lights and the materials, and whether you do some path guiding as well, because since you have the cache of spherical harmonics, you have some directional information in the scene of where the light is coming from. Is that something you've played around with?
So we wanted to apply more advanced, just path guiding over register, but for building this path tracer, we really need to start it from scratch. So we didn't explore that much. So but it would be a nice direction to pursue. Next.
Okay, thank you.
Okay, our last one. Could you elaborate on the grouping of the planoxos? It wasn't immediately obvious what you use for grouping.
Mm-hmm. So we need to carry the radiance for those nearby pixels in the screen space, but actually when we follow those voxels, they are in the memory layout, they are stored in different locations that they are scattered around. So if we perform the computation based on these screen pixel locations, they are not really locally grouped. So before actually performing the inference, we check the location of those voxels and we sort them, and we group nearby voxels in world space. Therefore, we could improve the memory locality.
Thanks for the explanation. Any more questions?
Hi, thanks. Great talk. I'm curious how the NRC would perform on mobile when you have hardware for large matrix multiplication. I'm guessing you don't have any info on that. Mm-hmm. But have you tried any other spatial data structures for the Radiance caching as well, like GPU hash maps or something like that? Because you said planoxels, right? Did you try it with...
No. We only tried MLP.
Right.
But regarding the first your comment, so actually now mobile vendors are to started support these metrics. But as far as I know, they only work efficiently for those in the quantized space. So if we apply them to with the flood precisions, we don't have much gain. So probably it might not be that efficient on our application still.
Fair enough. Thanks.
Second small question. Which order of spherical harmonics do you use, and have you noticed like diminishing returns? How did you choose up to which order to go?
So we only use this second order. So we only use the 9 coefficient. And we didn't go further, but if we reduce the spherical coefficient degree, then basically it's more like just learning diffuse term only. So in that case, so if we use a very close scene, then we don't have a specular highlight anymore. So but in terms of computational complexity, we couldn't go further. So we chose 9. In this case.
Okay, thank you.
Let's thank the presenter one more time.